Hey everybody, my name is Jeremy Cobb. Our team name is We Came, We SAWS, We Conquered, and our project is Preventing Sewer Overflow Events. Here is an introduction to everyone who worked on our project and the presentation. To the far left, we have myself, Jeremy Cobb, then we have Cameron Taylor, David Wederstrandt Sr, and then Ryan McCall. Next is a rundown of everything we're going to discuss during today's presentation. First, we're going to go into an introduction to San Antonio's water system. Then we're going to go into our executive summary, talk about where our data came from, what questions we asked the data, what factors from our analysis are valuable, how we made our predictions, how our machine learning model works. Then we're going to go into our recommendations, and then finally our conclusion. So, San Antonio's water system, why is it important? Well, between the years of 2006 and 2011, the Environmental Protection Agency recorded over 2,200 illegal sanitary sewer overflow, or SSO, events. These 2,200 SSO events resulted in over 23 million gallons of raw sewage spilling into our local waterways. This affects our community, with raw sewage ending up in our drinking water sources, and also when an SSO event occurs, raw sewage would dispense into our streets, ending up in our yards, potentially in our homes, and physical contact with raw sewage leads to a higher risk of gastrointestinal illnesses. In 2012, San Antonio paid $2.6 million in civil penalties to resolve these various Environmental Protection Agency violations. And in 2013, San Antonio agreed to a $1.1 billion budget in accordance with the Clean Water Act of 1972 to upgrade our sewer systems. With these upgrades scheduled to come to a completion by 2025, San Antonio is now allocating over $300 million a year in operations and maintenance of our sewer systems. So, how can we predict why a sewer incident happens? We take drivers such as rainfall, sewer maintenance, sewer age, and the temperature of the weather. We use it to predict root causes of sewer incidents that are found in the data. These root causes are things such as structural damages, liftgate malfunctions, and grease blocked pipes. We explore our features, we ran statistical tests, and what we ended up with was a decision tree classification model that had a 41% improvement over our baseline predictions. What we want to do with this model is present to SAWS to help them take preventative measures before more problems occur. We also want to use it to help San Antonio's water system have a faster diagnosis of sewer-related issues. Now, going into the acquisition portion of our presentation, let me introduce Cameron.
Thanks, Jeremy. We got our data from a few different places. First, we got the sanitary sewer overflow, or SSO, data from SAWS itself. This included just under 3,200 different SSO events. Next, we pulled in weather data from the NOAA. This was gathered at San Antonio's International Airport and was gathered between the years 2009 and 2019. Next, we pulled in 311 call data from the city of San Antonio. 311 is a service that allows residents to make calls to complain or ask questions about the city. So once we had our data, we had to join it together before we could use it for exploration. First, we were able to join the sewer and weather data by aggregating over days and then joining on the date of the SSO event. Next, we used a Python module called GeoPy that allowed us to extract zip codes from the street addresses that we were given with the SAWS data. SAWS only collected street number and street name rather than additional location data that we felt would be useful, but we'll talk about that later. On the right, you can see a map of the city of San Antonio that shows the most common root cause by zip code. Now, once we used GeoPy, we actually noticed that about a third of the results we were getting back were unusable. So rather than joining that together and losing a third of our data, we felt it would be better to keep as much data as possible and not use the 311 data at all. Next for exploration is David. Take it away.
Thank you, Cameron. Like Cameron said, we had our data. So what do we do with it? Well, we were now able to begin exploring. So what questions did we ask? For the NOAA weather data, we had questions such as, are SSO events triggered by the amount of rainfall? Or, does temperature trigger SSO events? For the sanitary sewer overflow, or SSO data, is the age of a sewer something that can be used to predict SSO events? Combining and using these data sets, we were able to statistically confirm our hypotheses and then visualize our findings. Quick note, for the next 3 slides, our visualization's x-axis or bottom axis is each of the most common root causes. Our y-axis is what we evaluated as a predictor for SSO events. As I said, with our data now combined, we were able to ask questions such as the first one we ask here. Is rainfall a relevant predictor of SSO events? The y-axis, or vertical line on the left side here, is the amount of rainfall in inches. Notice that following the y-axis of each swarm plot, the shapes are relatively uniform, with the exception of the highlighted events. Since each little dot represents an SSO event, we can see that lift stations malfunction more often when it rains heavily. And surprisingly, rain damages, well, they're more probable when it rains. The next question we ask, is temperature a relevant predictor of SSO events? We are now looking at temperature in degrees Fahrenheit. We can see that the data is pretty uniform, so temperature is not a good predictor of root cause. A final question we ask, is age of a sewer a relevant predictor of SSO events? We are now looking at age of sewer in years. We see here that relatively low occurrences of failures in sewers between 15 and 20 years of age for debris, rain, and grease contrast with the higher occurrences of failure in lift stations, narrowing down the likely cause of an event. And in this visual, we can see that sewers that suffer structural failures usually fail within the first year or after the 20-year mark. And with all this information, we can tell that age makes a good predictor. I will now be followed by Ryan to walk us through our model.
Thanks, David. So, how do we make our predictions? Well, in this case, we decided to go with decision tree classification. But how did we choose this? Well, first, we created a baseline model that predicts that every single event is caused by structural failure, because it was the most common out of our 11 root causes. It had a 39% occurrence, which means that model would have a 39% accuracy. We then tested several different models, like the decision tree classifier, which asks yes or no questions of the data to classify the event, a random forest, which is several decision trees stacked on top of each other, and k-nearest neighbors, that takes an unknown data point and compares its proximity to known data points to classify the event. We then picked the best model based on its performance on unseen data, and that was the decision tree classifier because it offered an improvement of 41% over the accuracy of the baseline. Now, how does our model actually work? Well, here is a diagram of our actual model, and you can see, even if we zoom in on this top part up here, there's a ton of information, and it gets quite complex. So let's simplify it. Here we're going to look at a snapshot of just some of the decisions that our tree makes. First, it asks a question like, was there more than half an inch of rain that day? If there was, the root cause was most likely a rain event. But if not, did the event involve something other than a sewer pipe? If it did, then it was probably lift station failure. But if not, is the sewer older than 36 and a half years old? If it is, then it was probably structural failure. But if not, is it a non-gravity sewer? If it is, then it was probably grease buildup. But what can we do with that information? Well, we can actually construct these checklists here that show us distinguishing features of each of these root causes, and then apply that information to new sewers. Take this sewer right here, sewer number 13. We have several pieces of information about it, and we want to know what it's most at risk of suffering. So first, we're going to look at its age. At 40 years old, that puts it most at risk for structural failures. With a pipe diameter of 42 inches, that puts it again at risk for structural failures. With a pipe length of 350 feet, it's at risk for structural failures and rain events. And it's a siphon type sewer, which puts it at risk for structural failure and grease buildup. Now with that information, we can clearly see that it's most at risk for structural failures. And now SAWS can apply an action plan to this sewer to treat it for future structural failures. Now I'm going to hand it off to Cameron to take us through our recommendations.
Thanks, Ryan. First, we felt that if we had more complete location data from SAWS, we could use it to build an even better model. For instance, if we were able to join in 311 data on zip code as we originally intended, we'd be able to use additional features, such as the amount of calls that came in a given zip code, and the response rate to those calls. Next, we feel it's important to use all of the sewer data, rather than only the sewers that have already experienced SSO events. If we had this additional data, we would actually be able to create a model that could predict when an event might occur, rather than only why it did. Finally, we feel it's important to implement our model to develop a playbook of sorts that uses our model's output to prioritize maintenance and upkeep of the city's sewers. With these recommendations in mind, these are the next steps we feel should be taken. First, developing the playbook implementation. Second, gathering all of the sewer data. Third, including the 311 data. And fourth, creating the on-site diagnosis checklist that Ryan talked about. Finally, present all of this data to SAWS itself so hopefully they can implement it and save our city some money in the future. We actually will be presenting our data to SAWS in the upcoming CivTech Datathon. This concludes our presentation. If you have additional questions or want to reach us, we have a link to our Codeup alumni page and our project repo on GitHub, as well as our personal profiles on GitHub and LinkedIn. Thank you all very much.